Inside your body, a high-speed assembly line is constantly processing materials to keep you alive. At any given station in this factory, the speed of production depends on two specific things: the raw materials coming in and the workers available to handle them. In biological terms, these workers are proteins called enzymes. As biological catalysts, they speed up chemical reactions without being consumed. We track this through a simple equation. A substrate, the raw material, binds with an enzyme to create a product. This interaction is highly specific, often described as a lock and key model. Every enzyme has a uniquely shaped active site designed to fit one specific substrate. If the key doesn't match the lock, the reaction simply won't happen. A successful reaction follows a set timeline. First, the substrate approaches the enzyme. Second, they bind at the active site to form a complex. Finally, the chemical transformation occurs, and the finished product is released. This precise physical fit allows your cells to perform complex chemistry at incredible speeds. Without these catalysts, your body would require high temperatures or intense pressure to trigger the reactions necessary to sustain life. Even with a perfect fit, every reaction needs a push to get started. This initial investment of energy is known as activation energy. This graph tracks the energy levels throughout a reaction. Think of the energy spike on the right like the steep ramp facing the skateboarder on the left. Without a way to lower that peak, the process is slow and requires significant effort to overcome. Enzymes work by physically lowering this energy barrier. By stabilizing the substrate, the enzyme reduces the activation energy required, much like shrinking the height of that ramp. The result is a reaction that proceeds much faster and with less effort. It is important to note that the enzyme itself remains unchanged. Because it is a facilitator and not a reactant, it isn't destroyed. One single enzyme can be reused to catalyze the same reaction over and over again. Because enzymes lower the energy requirement without being used up, a small concentration of them can handle a massive amount of chemical work across the entire system. Since enzymes are reusable, we have to look at what happens when the balance between workers and material shifts. What happens to the speed of the system if we flood it with substrate? Here, we're plotting the rate of reaction against substrate concentration. With 5 enzymes and only 2 substrates, the rate of reaction is low. As we add more substrate, the rate begins to climb because more workers are being put to use. When we reach 5 substrates for our 5 enzymes, every active site is occupied. The system is now operating at its maximum possible speed for this specific number of workers. Consider what happens if we keep our enzyme count at 5, but we triple the amount of substrate. The line on our graph flattens out. Even though there is plenty of raw material, the extra substrates have to wait for an active site to become free. The system has reached a hard physical limit. This horizontal line represents the saturation plateau. It marks the point where every available enzyme is working at full capacity, and adding more substrate can no longer increase the speed. This logic also works in reverse. If you have a limited amount of substrate, but you keep adding more and more enzymes, you will eventually hit the same kind of plateau. In our factory analogy, hiring 100 extra workers doesn't increase production if there is only enough material for 2 people. Those extra enzymes sit idle, representing unutilized capacity that cannot speed up the process. Mastering your exams means connecting 3 views: identify the lock and key fit, visualize lowered activation energy, and recognize maximum rate at saturation. When graphing reaction rates, pay close attention to the plateau. Drawing that horizontal line proves you understand biological machinery has physical limits. Understanding these concentrations provides a clear view of metabolic efficiency. By calculating the physical limits of the lock and key model, you can predict exactly how fast these biological assembly lines can run.